Imagine you're sitting in the control room of a refinery. Thousands of sensors are sending data every second. Temperatures, pressures, flow rates, compositions. Suddenly, an AI system flags that a heat exchanger is about to foul in within 2 weeks. It recommends adjusting the operation conditions today to prevent a shutdown later in the future. Do you trust it? More importantly, if AI can predict failures, optimize processes, write reports, generate code, even answer engineering questions, then where does that leave chemical engineers? Will AI replace us? Or is the real story much more interesting? Every generation of engineers has its "this will replace us" moment. When calculators showed up, engineers worried. When spreadsheets came along, engineers worried. Aspen Plus, MATLAB, full-blown process simulators, advanced process control. Each one of these, at some point, was going to make engineers obsolete. But none of these tools actually eliminated engineers, did they? What they did was change how engineers worked. We stopped manually solving flash calculations by hand and started designing bigger and more ambitious plans. We stopped drawing PNIDs by hand and started designing more complex systems because the manual bottleneck was gone. Each one of these tools shifted our attention from the grunt work to the harder problem underneath it. And now artificial intelligence is knocking on the same door. And the question isn't whether it will change the job. It will. The question is, what's it going to free us up to do next? Let's first take a look at exactly how AI started to change the game. Talk about predictive maintenance. Instead of waiting for equipment to fail, AI is able to detect patterns that humans miss. Vibrations, temperatures, acoustic signals. Small deviations buried in the noise that no engineer is going to catch just by eyeballing a trend line. But AI catches them. And then maintenance stops being reactive. It becomes proactive. You fix the bearing before it seizes, not after. Now look at process optimization. In my limited experience, one major issue I've seen is that people don't want to change what's working. I mean, if it ain't broke, don't need fixing, right? However, the downside of this is that the process actually runs suboptimally when in fact there exist far more efficient ways of running the plant. Now, AI brings in a significant advantage of efficiency here. It can evaluate thousands of possible scenarios and test them for safety in a very short span of time. Instead of running at one operating point, which someone picked up years ago and hasn't changed since, AI evaluates thousands. Thousands of combinations, continuously looking for the one that saves you the most amount of steam, cooling water, electricity, raw materials, and all kinds of resources. One of the most exciting developments as a result of this integration of AI is the rise of digital twins. These are essentially virtual replicas of real plants that are updating continuously with live operating data. Practically, AI can test operating strategies on the digital twin first before recommending it for the real plant, thus reducing risk, while uncovering opportunities that engineers may never have considered. Another interesting thing is soft sensors. Some variables just can't be measured continuously. Too expensive, too slow, too physically awkward to instrument. AI estimates them instead, inferring a value you can't directly measure in real time from the variables that you can. This isn't just a lab concept, it's already happening on real plants right now. Of course, AI is aiding tremendously in research as well. Scientists can screen catalysts, predict molecular properties, design experiments at a speed that once would have taken years. The bench to plant timeline that once used to define entire careers is now significantly shrinking. And you know this one well, the offices are benefiting too. It's not glamorous, but engineers spend an enormous amount of time compiling reports, searching manuals, generating code, summarizing incidents. AI saves hours every week. Now looking at all this, we see that AI is quite capable across maintenance, optimization, sensing, research, even paperwork. But here's the catch. In every example we've talked about, there's always been a human somewhere in the loop. See, AI recognizes patterns, but engineers understand the system. AI is incredibly good at optimizing an objective. Engineers decide what the objective should be. Maximizing production sounds great until you remember you have to stay within equipment limits, meet product specifications, satisfy environmental regulations, minimize energy consumption, and above all, operate safely. Chemical engineering has never been about maximizing one number. It's about balancing dozens of competing constraints at the same time. And deciding which trade-offs are acceptable is still a human responsibility. Let's take an example. Suppose we have a reactor. The reactor's temperature starts climbing exponentially. AI might suggest reduce the feed rate, a reasonable response based on patterns that it's seen before. But the engineer's first step is different. They ask why. Is the sensor faulty? Has the catalyst changed? Is cooling water unavailable? Is there fouling? Is this the start of an exothermic runaway? Same data, but the reasoning goes further. From noticing the pattern to identifying the cause. That's what first principles thinking gives you. Mass balances, energy balances, thermodynamics, fluid dynamics, reaction engineering. It's the basis of reasoning about what's actually happening in a system rather than just responding to what a model outputs. There's another reason why engineering judgment still matters. Uncertainty. Every AI model is built on assumptions. It's trained on historical data, on operating conditions it's seen before, on sensors that it assumes are working correctly. But chemical plants have an annoying habit of doing things they've never done before. Feedstock quality changes, equipment changes, instruments drift, a valve sticks, a pump starts cavitating, the weather changes, or sometimes something simply can happen that no one's ever seen before. It's like a 0 day. That's exactly when engineering judgment becomes the most valuable. Because when the system moves outside the world that the model is trained on, someone still has to reason from first principles and figure out what exactly is happening. And this matters most in safety critical situations. A model's output is a statistical estimate. Physical reality isn't. If a valve is closed, it's closed, no matter how confident your model sounds. That's the part of the job that AI doesn't replace. Someone still needs to reason from the physical system itself, not just from the pattern. See, chemical plants aren't software. They're people, operators, technicians, shift engineers, maintenance teams, safety officers, managers. Let's take another example. Let's say AI suggests increasing throughput. Before acting on that, the engineer will ask a different set of questions. Can the downstream unit actually handle it? Will operators have enough time to respond if something goes wrong? Is maintenance scheduled for tomorrow? Does this push the plant beyond its environmental permit limits? Notice that none of those questions are purely technical. That's the point. They're technical, economic, human, environmental, ethical, all at once. AI can certainly help evaluate many of these factors, but deciding how to balance them and ultimately taking responsibility for that decision, that still rests with humans. Maybe that's the biggest misconception. We often ask whether AI can make better decisions than engineers, but that's rarely the choice. The real question is whether engineers equipped with AI can make better decisions than engineers that aren't. And I think the answer to that question is yes. The future isn't engineers versus AI. It's engineers working alongside AI, bringing together data-driven insights, experience, physical intuition, and judgment to solve problems that neither could solve as effectively on their own. So what does this mean practically? What should you actually be learning? Not learn AI, that's too vague to act on. Instead, learn how to integrate AI into your work. Learn the tools. Learn the math behind why it works. Learn Python. Learn statistics. Learn data visualization. Learn the basics of machine learning. Learn prompt engineering. Learn automation. These are practical, learnable skills and they will make you more effective day after day. But in the process, don't sacrifice your fundamentals to make room for these new skills. Thermodynamics, process control, transport, process design, reaction engineering. Those aren't optional, they aren't old-fashioned. They're what let you judge whether an AI's output is actually right. Not just fluent, not just confident, but contextually right for the situation that you're currently dealing with. That's the combination. The technical fundamentals plus the new tools. Not one replacing the other, but working together. The future doesn't belong to engineers who ignore AI. Neither does it belong to those who blindly trust it. It belongs to engineers who understand both, who know when to automate, when to question, and when to rely on first principles. Because in the end, chemical engineering has never been just about making calculations. It's about making decisions in the real world, where safety, sustainability, economics, and people all matter. AI can definitely help us make better decisions, but the responsibility still belongs to the engineer.